Hello again. In this video, I will be explaining my problems from topics 5 through 12. So topics 5 through 8, I did 3 slip and slide problems, and I will start by explaining those. In the first slip and slide problem, the goal was to solve for the volumetric flow rate exiting the tube of the slip and slide through the holes. This is an example of both the extended Bernoulli equation and fluid flow with friction loss. So we start with the extended Bernoulli equation. The problem statement tells us that the hose is horizontal, so this goes away, and I forgot to cross this out, but d work non-flow dm is also 0, which simplifies it down to your delta p's, your delta v's equal to your negative friction. And then we know that for this kind of problem, we can sub in this equation. So then by taking this out and just equating these to each other, we are able to rearrange the whole equation to solve for V2 squared and then also for V2. And so that is the rearrangement, and then this would be V1 squared, but we don't know the velocity, but we do know the flow rate in liters per second. So we can do that converted into meters cubed over the area, and that will be equal to our V1 squared, which will give us our V2 squared, which when we take the square root of will give us this. And then back up to the relation between velocity equals q over a. So we solved for this velocity, which means now we can do velocity times area and then divide it by 1,000 to get it into liters. In the answer key for this problem, I originally forgot to add in the V1 squared, and so the answer key is wrong and does not give this answer. And then just to clarify, this is equal to V1 squared because I'm using the area of the hose, which is why this diameter is different right here. And then down here, it's the area exiting the holes of the tube, which is why it's 0.5. Second slip and slide problem asks to find the drag force on a ball that is accidentally thrown into the slip and slide, and this is an example of external fluid flow. So first of all, the Reynolds number has to be solved for, and so that's rho d v infinity over mu, and so the v infinity is just the relative velocity of the object to the fluid, so that is that there because 0.95 is at what speed the ball was thrown into the slide at. So we calculate our Reynolds number, which is between 5 and 1,000, and we have to do this because fluid flow over a smooth sphere like this has different CD equations depending on the Reynolds number, and so once we know what the Reynolds number is, we can choose which CD to use. Which I have done here, and then that can all be plugged in to the equation for drag force, and everything in this equation is already known, so it's just really simple to plug it all in and solve and get 1.22 newtons. Third slip and slide problem asks to solve for the VSMF of the system if instead of having this normal slip and slide pad at the end, if there was a catch area of like the couche strings from the play balls that kids play with a lot. And so due to the material of the strings and the way that the problem is set up, you could assume that that pad with those strings is a fluidized bed. So then with the assumption of the fluidized bed, we know that this is an equation that we have to help us solve for VSMF in those situations. And then we have a squared variable and a normal one, and we have terrible coefficients out in front, and so I said to let this equal to A, this equal to B, and this equal to C, because then you're able to do the quadratic formula after you know what all of those are. And then, so the VSMF for this system is 0.00296 meters per second. In the last part of this video, I will be talking about my problems for topics 9 through 12, which are a hairspray can and paint mixing. So for the hairspray can problem, it is an example of a compressor, and it is asking us to find, with certain conditions in the exit Mach of a rocket, what is the Mach number at the inlet. So we know that the Mach is just the velocity over c, and then we know for c it is kRt. And then in the problem we are told that hairspray is or can be approximated as CO2, which then we can assume is an ideal gas. So for an ideal gas only, K is equal to delta P, which is nR delta T over V. But we don't know anything about our moles or our volume, but we do know all of this information. So we use the substitution of N over V is equal to rho times velocity over molecular weight. And making that substitution, we're able to solve for C, and then we're given the velocity, and so just velocity over C will give us the Mach number, which is 0.295. This problem is about a fluidized bed that is used to mix paints, and this covers topics 10 through 12. And so the goal of this is to use Navier-Stokes to come up with an equation for the velocity profile, and then to use that equation to solve for the velocity at different x points. So we start with continuity, and we get rid of this because it's steady state. We get rid of this because the problem statement told us it was parallel flow, and we get rid of this because the problem statement told us that it is a very wide bed. And so continuity will tell us that dW dz is equal to 0. So then we go to the z component of Navier-Stokes. This again goes away because of steady state. This goes because of parallel flow. This goes because it is wide, and this goes from the continuity equation. On the other side of the equation, this goes away because it is open to atmosphere, and the delta P is considered 0 because gravity is the driving force. So that stays in. And then over here, this is the only one that is not able to be taken out. This goes away again because it's wide, and this goes away again because of continuity. So then from there we can rearrange the equation because it's this little part is all equal to 0. So that's what I have here is I have negative rho g over mu equals d2w dx2. And so you integrate that once, and then twice you'll have two constants, which then you need to solve for. And so those are solved for using boundary conditions, and the boundary conditions we have is that the velocity is 0 at x equals 0 and x equals 1, and this is because of the no-slip boundary condition at the walls. So then using those boundary conditions, we know that C2 is 0, which then allows us to solve for C1, and then we have our full velocity profile equation, which then gets us to be able to solve. We already knew that x at 0, or the velocity at 0 is 0, and then the velocity at 0.25 is 33.1 meters per second, and the velocity at 0.5 is 44.2 meters per second, which makes sense because 0.5 is the middle as the x length is 1 meter, and so that's where it should be the fastest.